And our next speaker is Ashkan Zarsour from MIT. And he's going to talk about risk contours map for risk-bounded motion planning under perception uncertainties.
Thank you. Hello, everyone. In this work, we introduced risk contours map for risk-bounded planning under perception uncertainties. In this problem, we have probabilistic uncertainties in location, size, and geometry of obstacles, and we define risk as a probability of collision of robot with such uncertain obstacles in the environment. Now, in such framework, and instead of working with an ordinary map that only shows free and obstacle regions, we suggest, due to lack of precise information of obstacles, we construct a new map that we call it risk contours map. Such map represents risk information of different region in environment. To construct such map, we define the notion of delta risk contour, which is a set of all points in the environment whose risk is less than or equal to delta. Then risk contours map would be a collection of such delta risk contours with different risk levels delta, as shown here. Now, we can use such map in risk-bounded motion planning. In risk-bounded motion planning, we are looking for a trajectory PT to connect the given initial and goal points in the state space, and due to uncertainties, we have probabilistic safety constraint. Probability of collision of trajectory with uncertain obstacles in the environment should be bounded by predefined value delta. Now, we can replace this probabilistic constraint with deterministic constraints in terms of delta risk contours of obstacles. And as a result, we can call any motion planning algorithm like RRT star or PRM to construct the trajectory. As shown here, we only need to make sure that obtained trajectory is always inside the delta risk contours of the obstacles. Now, in this work, we are going to provide a general and systematic numerical procedure to construct delta risk contours for given uncertain obstacles. We describe such obstacles with the polynomial level sets with uncertain vector omega. In general, such set represents a non-convex obstacle with probabilistic uncertainties in the environment. And also, provided technique is general, and it can deal with both bounded and unbounded probability distributions of uncertainties. And it only uses a finite sequence of the moments of probability distributions to construct delta risk contours. Constructing delta risk contours is challenging. From its definition, we need to deal with probabilistic constraint. Here we have a multivariate integral with respect to probability distributions of uncertainties over non-convex region of obstacles. In general, such integral doesn't have any analytical solution, and hence it's challenging to deal with. The main idea in this work is to find a polynomial approximation of such probabilistic constraint and use its level sets to represent delta risk contours. More precisely, we are going to find a polynomial such that its delta sublevel sets represents the inner approximation of the delta risk contours, as shown here. And similarly, we are going to find a polynomial such that its 1 minus delta superlevel sets represent outer approximation of the delta risk contours of the problem. And to find such polynomials, we are going to leverage theory of measures and theory of moments, and also theory of sum of squares polynomials. And we are going to provide a convex optimization in the form of semi-definite program to construct such polynomials. We also show that as the order of polynomials increases, these inner and outer approximations converge to the true delta risk contours of the problems. We have different set of examples, like planning in presence of human crowd that behaves randomly. Happy to discuss these examples and also mathematical details in the poster session. Thank you.
A little bit on the difference of your approach compared to a convolution of an occupancy grid map and planning in a convolved map.
The risk map, you mean?
Yeah, just a map which you convolve with the kernel
Okay,
and
so
then plan in that map.
the existing methods are mainly limited to Gaussian uncertainties and linear and convex description of the obstacles. But here, so we are general, we don't have such limitations. So we can deal with nonlinear, non-convex regions, almost arbitrary probability distribution. And also, we provide a systematic numerical procedure. So we formulate this problem as a standard chance constraint optimization and then leverage the techniques. This is the main difference.
But couldn't you convolve with a non-Gaussian kernel?
Yeah.
Yeah, I have a question for this. Right, I have a question for the same here. Hey. Yeah, okay, I have a question for the same speaker. I really like the idea of this having, risk boundaries, but I'm wondering whether this risk boundary should depend on the dynamics of the vehicle, or if it is a vehicle, as well as its geometry and other things, right?
Yeah, so this is a good question. So in general, we have two main sources of uncertainties. The one that comes from environment and the other one that comes from the system itself, dynamics. Here we only consider the environment uncertainties. And in fact, we are generating nominal risk-bounded trajectories for the robot to follow. Then in the next step, when we are designing controllers, we can consider dynamics and uncertainties of the system itself to follow these generated trajectories.
Sorry to ask the same question, same speaker. There are a variety of notions of risk. So, is your framework for like confidence intervals or chance constraints, or you can do also like conditional value at risk and other kinds of risk notions? There are a variety of risk metrics out there.
Right. So we are here. So we here. So using the standard formulation of the risk. So given probability distribution and some regions, how we can find the probability of, let's say, collision. But we can generate these techniques to other notion of the risk.
Hi, sorry to pick on the same speaker again, but I was just wondering if you could maybe try to draw some similarities or differences between what you presented and like stochastic reachability.
Sorry, I didn't get the question.
Sorry, I'm asking if there are any similarities or differences between your work and like stochastic reachability.
Yeah, right. So in the reachability, so we need to deal with dynamics and its uncertainty. So we can actually use the same methodology to find the reachability sets given the nonlinear dynamics and the nonlinear different uncertainties. So it's kind of the same. I'm actually addressing this problem in my other papers, how we can use the same methodology to find a forward and inverse reachability set of nonlinear system.
Yeah, any further questions from the audience?